Hello and welcome to Equity Education, the chemistry version. And today we're going to be looking at entropy and Gibbs free energy change. So I'd like you to open up your booklets and we will get started. Okay, so entropy. So we can describe entropy as the measure of disorder of or in a system, and technically it is the energy that's in the disorder of a system. I don't really want to go into so much detail about the technicalities of entropy. This will do for now. We'll talk about it a little bit later on. Okay, so units. Units are important. Is J to mole minus 1 to K minus 1, which means the energy required to increase the temperature by 1 Kelvin per mole of whatever it is. Yep. So the more disorder in a system, the greater the entropy. So the more disorder in a system, the increase in entropy. And let's see if you can work this out. So what changes in state would lead to an increase in entropy? Have a quick think about it and see if you can get the answers. Okay, and I assume that you've written, I would guess, that solid to a liquid and liquid to a gas. And we can explain it by saying, because there is more freedom of movement in a gas, it is highly disordered and the particles move anywhere, therefore increasing the energy in the structure. Solids have low entropies as particles cannot move around as much, generally only vibrate. Okay, so it's this freedom of movement which gives the in a gas that they can move anywhere, which means that the energy can be increased because they're bashing into each other, going slow, they're going fast, they're going anywhere, and it's this disorder which is created, not created, but is in the system, that we give this value entropy. Okay, so that's as far as I want to take it in the technical terms, but you get the idea. So the more disordered a system, like in a gas, the greater the entropy. Okay, so moving on. So if we have a temperature increase, will also produce increase in entropy, which isn't surprising, as particles will have more kinetic energy, so they have more freedom of movement and can move around more, and along with a solid dissolving in a liquid. Again, the solid, the particles or the ions, whatever is in the being dissolved, will be able to move around a lot more, so it will increase entropy. Okay, so another question for you: why would the entropy of the system increase or decrease in the following reaction, and why? Okay, have a go at answering that, and I'll see you in a second. Okay, and I'm sure you've got the answer. That in fact the entropy would increase. Why would it increase? Well, we're producing two products from one. So that increases the degree of disorder. And one which is a gas. Therefore, a more disordered state. Okay, so the entropy would increase because we're producing two products instead of one, from one reactant, and one is a gas, therefore there's going to be more disordered state. So if you get a question like this, see how many products there are and see if any are gas or changes from states. Yep, increase from, if we go from solid to a liquid, entropy will increase. If we go from a liquid to a gas or a solid to a gas, entropy will also increase. Okay, so entropy change in a reaction. So substances can be assigned an entropy, which means because they have internal energy within the structure, so we can give substances, any substances, a value for entropy. So this means we can calculate the entropy change in a reaction by, so my delta S, the energy change, entropy change in a reaction is the sum of the entropy of the products in the standard states, in standard conditions, minus the entropy of the reactants. Okay, e.g., what is the entropy change of the decomposition reaction? NaCl goes to Na plus half Cl2. You should be able to calculate this, so have a go at doing it and then we'll go through it when I get back. Okay, I'm sure you've managed to do this, so all I'm going to do is my entropy of the products minus the reactants. So my delta S would equal 51 plus 223 divided by 2. And we're dividing by 2 because it's 1 mole of Cl2 here. We're only using half Cl2 here. I'll put it in brackets. So this is my reactants minus 72.4, which is my this is my products minus my reactants. I always do that. Let's get it the right way around. So equals 90.1 joules per mole minus 1. Okay, minus 1. So we have a positive entropy, and that equates to this equation as well. So we're going from one reactant to two products. One of them is a gas, so there should be a positive entropy, which there is. Okay, so discussed entropy. Now we're going to talk about free energy, and free energy is given the symbol as delta G, and we can calculate free energy using Gibbs equation. So delta G equals delta H minus T delta S, and our units, so delta G as units of kilojoules per mole minus 1, delta H kilojoules per mole minus 1, so you already know, I'm sure you've seen that before, whereas my entropy is joules per mole per Kelvin, which means I always, when we're doing these calculations, have to divide by 1000 to get it into kilojoules per mole minus 1. So don't forget to do this. This is important. This is really the only reason why students make mistakes when they're doing these calculation questions. Okay, so moving on. So what is the Gibbs equation? So the Gibbs equation allows us to calculate the amount of useful work that can be done by a system, and it allows us to work out whether a reaction is feasible at the stated temperature. So if delta G is negative, the reaction is feasible. It's feasible. I can't spell feasible. Spell it right. At that temperature. If delta G is positive, it is not feasible at that temperature. So remember, we're talking about a reaction, yeah? So a negative delta G means the reaction is feasible. Sometimes you might see it called spontaneous. We'll stick with feasible for what will be described later as why we use this word instead of spontaneous. Okay, so moving on. So there are 4 scenarios for any reaction. We'll go through these scenarios. So delta H is negative and delta S is positive. So that means the reaction is exothermic and entropy has increased. This means delta G will always be negative and therefore the reaction is feasible. And if we think about it quickly, so if we have delta G equals delta H minus T delta S, so delta H will be negative and minus T delta S will be negative. So delta G will always be negative, so it will always be feasible. Okay, moving on. Delta H is positive and delta S is negative. So the reaction is endothermic and entropy has decreased. This means delta G will always be positive and therefore the reaction is not feasible. And this can be explained as both delta H and minus T delta S are positive, e.g. let's do this quickly, delta H will be positive, minus T delta S, this part will be positive, therefore we're always going to get a positive delta G. Okay, so when you say positive T delta S, it's the minus T delta S, yeah? So you have to include the minus. Okay, moving on. So 3, when delta H is negative and delta S is positive. There's no clear answer. It's both delta H and minus T delta S are negative. So you need to do the calculation. And again, when delta H is positive and delta S is positive, there is no clear answer, as both delta H and delta S are positive. You need to do the calculation. Don't know why I wrote that twice. Okay, so and then I've got this diagram for you to make it a bit more simpler. Okay, so if delta S is above 0 and delta H is below 0, so we're talking about negative or positive, it's always feasible at any given temperature. If delta H is above 0 and delta S, excuse me, just for 1 second, let's get this right. Okay, you may have noticed that I put a delta H here instead of delta S. I was wrong. So where was I? So if delta H is the entropy change, delta H is above 0 and delta S is less than 0, it's never feasible at all temperatures. And then the 2 bits in between, so the calculations. So if delta S is below 0 and delta H is below 0, it's generally feasible at lower temperatures, but you still need to do the calculation. And the opposite, for delta H above 0 and delta S less than 0, it's feasible at high temperatures in general, but that's just a recommendation. That's not the right word, but you know what I mean. Yeah, so you're still going to have to do the calculations. And that's what we're going to move on to now. So, calculating free energy changes. Right, so I'm just going to write down our formula again. So, delta G equals delta H minus T delta S. And we have an example. And I think you're going to be able to do this on your own, so I'd like you to have a go at it, and then we will go through it together. Okay, hope you did okay. I did notice that I haven't filled these out, but you still should have been able to recognise which one's which because of the units. So delta H is plus 57.2 and delta S is plus 176 joules per Kelvin per mole. I've written it the other way around there for some reason. Okay, so what is the Gibbs free energy change for this reaction? So delta G, let's get used to writing it, delta H minus T delta S. So delta H is plus 57.2 minus 298 times by 176 over 1000, which gives me a value of plus 4.8 kilojoules per mole minus 1. Okay. Remember this value here? Yeah. So we've changed it to kilojoules. So what does the answer tell us? So it tells us the reaction is not feasible at this stated temperature. Okay, right, so these reactions are, we would say reversible, yeah, so they're reversible for most of them. So at equilibrium, would quickly describe it and then you'll have a go at doing it yourself. So if delta G is 0, the system will be in equilibrium. We can calculate the temperature. Equilibrium will occur if we know the delta H of the reaction, the delta S of the system. This is also the temperature the reaction is feasible for the purposes of this level of study. Okay. Often this reaction may be considered feasible at this temperature, but the reaction rate is so slow because the activation energy, that's my gap, is too high for the reaction. So at the start of this lesson I was talking about this word spontaneous, which you might see. Now I choose to use the word feasible because when we talk about spontaneous, it may be spontaneous and it may be feasible, the reaction, but it's so slow that it might not happen over such a long period of time, so it doesn't look like it's spontaneous. So we use the word feasible instead. Right. So what does that mean? So e.g., so that means delta G is equal to 0, which is 0 delta H minus T delta S. So I can rearrange this equation now so that temperature equals delta H over delta S. And this will give me the temperature, if I divide my enthalpy of my delta H over my delta S, give me the temperature, the minimum temperature for the reaction to be feasible. So, your turn now. So, e.g., calculate the minimum temperature required for the reaction to be feasible using the data below. Okay, so have a go at this and I'll go through it with you when you get back. Okay, I'm sure you will manage to do this, so let's have a go at doing it. So the first thing we need to do is we need to calculate the entropy change of the system. So calculate delta S, so my formula is delta S sum products minus sum my reactants, which gives me a value of my products are 238 plus H2O 189 minus CO2, which is 214 plus 3 times 131. Remember, because it's per mole, we need to times by our molar ratio here, which gives me a value of something. What's it give me a value of? Minus 180 joules per mole per Kelvin. Next thing I need to do, so this is my number 1, don't forget to convert units. So 180 divided by 1000 equals, obviously, minus 0.18 kilojoules per mole minus 1. And lastly, calculate the temperature. And I calculate my temperature by saying, oops, delta G equals 0, therefore I get this equation. So I can stick it in, say minus 49 over minus 0.18, which gives me a value of 272 Kelvin. Okay, right, so short and sweet today, hope that was helpful. I think most of the calculations for Gibbs free energy are pretty straightforward, you should be able to do them. Yes, as I said, hope that was useful, and I'll see you next time. Okay, bye bye.